In this video, we discuss homogeneous linear ordinary differential equations with constant coefficients, We'll discuss the motivation or rationale behind the method. Then we'll talk about the general solution for second order homogeneous linear ordinary differential equations with constant coefficients. And we'll look at some examples. To get started, I would like to motivate the method with an example. So let's say you have a differential equation that looks like this. Y double prime minus 4 times y prime plus 3y equals 0. Well, this is a second order differential equation. It's linear because y double prime is raised to the first, y prime is raised to the first, y is raised to the first. It has constant coefficients. The coefficients of y and y's derivatives are 1, -4, and 3. And it's homogeneous because the right-hand side is 0. So this is a second order, homogeneous, linear, ordinary differential equation with constant coefficients. And the question is, what kinds of functions might satisfy this equation? Or in other words, what type of function can you take the second derivative of, then subtract 4 times the first derivative, and then add 3 times the function itself, and then have all of those cancel out? So you've got basically all the same types of functions multiplied by constants and added together so that all of them cancel out and you get a 0. When I ask this in class, students often don't know the answer to this question, but if I pose it this way, they often know the answer to this question because we've already studied first order differential equations. This is a first order differential equation that's similar. It also has constant coefficients. This is equivalent to this equation, y prime minus 3y equals 0. Now, when I first started this class, when I first start differential equations on the first day, when we're just talking about what a differential equation is and what a solution is, I almost always ask this question. I say, what function can you take the derivative of so that you get 3 times the function back? And sometimes I have to get rid of the 3 so that students realize that I'm talking about an exponential function. I say, what function do you take the derivative of so that you get the function back? Well, it's an exponential, e to the x would work. But if you have 3 times the function, if you want to get 3 times the function back, y equals e to the 3x turns out to work because the derivative of e to the 3x is 3 times e to the 3x. So that works. And then it turns out that if you multiply that by a constant, that also works. The derivative of a constant times e to the 3x is 3 times the constant times e to the 3x. So this function satisfies that differential equation. Now you can also think of it this way. Rather than thinking of it in terms of this differential equation, you can think of it in terms of this equivalent differential equation. What function can you take the derivative of so that when you subtract 3 times the original function, all the functions cancel, like all of the terms cancel, and you're left with a 0? Well, this exponential works that way. Similarly, I would expect an exponential to work here. Now here, we knew to use a 3 times x in our exponential because we were looking for a function whose derivative was 3 times the original function. And we know the derivative of e to the 3x is e to the 3x times the derivative of the inside, which is a 3. So when I saw that 3 there, I knew that there would be a 3 over here. Here, it's less obvious. It's less obvious what that exponent should be, but I think the principle still holds. The idea is still the same. If I've got a function like this, or excuse me, a differential equation like this, I'm looking for a function that you can take the second derivative of and then subtract 4 times the first derivative and add 3 times the function and have all of the functions cancel out and get 0. Well, the only functions that behave that way are exponential functions because the derivative of an exponential function, the derivative of e to the kx, is just that constant k times e to the kx. That's due to the chain rule. The derivative of e to some power is e to that power times the derivative of the inside. So we know that's true. So whenever I let y equal a function that looks like this, when I take the first and second derivative, I'll just get a constant times an exponential minus 4 times a constant times an exponential plus a constant times an exponential. And all the exponentials, because of the nature of these derivatives, are going to be exactly the same. And so we can pull the exponential out. And then for the right choice of exponential, all those constants could add together, all those coefficients of the exponential could add together and we could get 0. So that is the motivation or rationale behind this method. In general, if you see a constant coefficient, homogeneous, linear, ordinary differential equation, what I want you to do is I want you to let y equal e to the mx, and you're assuming that y equals e to the mx is a solution of this differential equation. And the reason is that reason that I just gave you over here, because the derivatives of exponentials yield constants times exponentials. And if I take constants times exponentials and I multiply those by constants and add them together, for the right exponential, I might be able to get 0. So we'll let y equal e to the mx for some unknown m, and we're assuming that this is a solution to the differential equation. So sometimes I'll just write let y equal e to the mx, but I'm going to be very, very explicit here, and I'll say let y equals e to the mx be a solution of the differential equation. If y equals e to the mx is a solution of the differential equation, then it satisfies this equation for the right value of m. To figure out what values of m, I'm going to take the derivative of this function twice and substitute into the differential equation. The derivative of e to some power is e to that power times the derivative of the inside by the chain rule. And then I bring the constant down, and the derivative of e to some power is e to that power times the derivative of the inside by the chain rule. So that gives us m squared e to the mx for y double prime. Now I want to substitute these into the differential equation in order to get an equation that must be satisfied by that constant m that we're looking for. So the differential equation looks like this. It's y double prime. Oops. Looks like I found a marker that's, or a pen that just doesn't work. And that's okay. It happens sometimes. So our differential equation is y double prime minus 4 times y prime plus 3 times y equals 0. And then if we're assuming that y equals e to the mx is a solution, then we have this. Y double prime is m squared e to the mx. And then y prime is m e to the mx. And y is e to the mx. And that equals 0. So if this is a solution to the differential equation, m has to satisfy this equation. And that equation is equivalent to this equation. Just factor out that e to the mx. And so we've got a product equals 0. That product equals 0 if this equals 0 or this equals 0. But e to the mx, remember what that looks like. That's never 0. If m is positive, it looks like that. If m is negative, looks like that. It's a decreasing exponential. If m happens to be 0, that's e to the 0, which is 1. Looks like that. So no matter what m is, look at the range of each of those functions. The range here is 0 to infinity. The range here is 0 to infinity. The range here is a single y value, and it's just y equals 1. So this times this equals 0 if this equals 0 or this equals 0, but this never equals 0. So the only way that this is true is if that polynomial function in m equals 0. So let's go back. What did we say? We said if we let y equal e to the mx, then m must satisfy this equation because y equals e to the mx is a solution of this differential equation. So y equals e to the mx will be a solution if this equation is satisfied by m. In order to find the values of m that satisfy this equation, we're just going to solve this quadratic equation. So that makes this one of the easiest methods in all of differential equations. If you can solve quadratic equations, you can solve these differential equations. If you can solve polynomial equations, you can solve nth order homogeneous differential equations. So we've got this polynomial has to be 0, and that's easy enough. In order to solve that quadratic equation, this one's easily solved by factoring, so I can factor. I need two numbers that multiply to give me a positive 3 that add to negative 4. Negative 3 times negative 1 is positive 3. Negative 3 plus negative 1 is negative 4. So this equals 0 if this equals 0. And the only way that this times this equals 0 is if the first factor equals 0. Oops. Or the second factor equals 0. And then if we add 3 to both sides, we get this. And if we add 1 to both sides, we get that. So we actually have two values of m that work, which is a very good thing. Because remember, this is a second order differential equation. And a second order differential equation has two linearly independent solutions. Since we have two values of m, and y is equal to m e to the mx, we already have two linearly independent solutions. So what this is saying is that if y equals e to the mx is a solution to this equation, the only way that will happen is if m satisfies this, and m satisfies this if m is one of these values. Now I'm going to call this one m1, and I'll call that one m2. So if m1 equals 3, the corresponding solution is y1 equals e to the m1x. That's e to the 3x. And then if m2 equals 1, that's a second solution to the differential equation. Y sub 2 equals e to the m2x. And if m sub 2 equals 1, that's y equals e to the x. So we have two linearly independent solutions of a second order differential equation. And that's what we need in order to have the fundamental set. So the fundamental set of solutions is e to the 3x and e to the x. So that means that the general solution is y equals y sub, or c1y1 plus c2y2, which is c1 times e to the 3x plus c2 times e to the x. And this will turn out to work for all real numbers. Okay, so we just solved a homogeneous differential equation. I hope you thought to yourself, that's not bad, because it's really not bad. It's not bad at all. But the key is this. If you have a constant coefficient homogeneous nth order differential equation, you're going to let y equal e to the mx. Because if you take derivatives of exponentials and you multiply them by constants and you add them together, they all look the same. Like all of these terms are going to be constants times e to the mx. You just have to find the right value of m that makes that true. So you let y equal e to the mx because it's a constant coefficient equation. And then you try to find the values of m that satisfy that equation, or that will cause this function to satisfy that equation. So you take the first derivative and second derivative, and then you substitute y prime, and y double prime into the differential equation. So let's write down the steps of the method. So we let y equal e to the mx, we compute y prime and y double prime. And you substitute into the differential equation. And then you simplify. And then after you substitute into the differential equation and simplify, you're going to end up with a polynomial equation in M. That's called the characteristic equation. In general, if you have an nth order differential equation, this will be an nth degree polynomial. So we have an nth degree polynomial equation that we need to solve for m. Then we solve the characteristic equation for m1 and m2. And we're just solving for m1 and m2 because it's a second degree polynomial. And it was a second order differential equation. So since it was second order, I have a second degree polynomial or a quadratic equation. So we solve the quadratic equation. This time we happen to get two real roots that are distinct from each other. And then if you have two distinct solutions, y1 equals e to the m1x is one solution, y2 equals e to the m2x, is your second linearly independent solution. So we're stating y1 and y2, and those come from substituting m1 and m2 back into that initial guess, y equals e to the mx, and then we state our general solution. And the general solution is y equals c1y1 plus c2y2, and this is true on the entire real line. Now that was just one example to motivate the method, but I hope that it helps you to understand the method a little bit. In order to move on from here, I want to do this more generally. And we're going to do this more generally and talk about the forms of the solutions for second order homogeneous linear ODEs with constant coefficients. We're going to look at higher order homogeneous linear ODEs with constant coefficients in a different video. So in general, let's say you've got a differential equation that looks like this. A times y double prime plus b times y prime plus c times y equals 0, or a, b, and c are constants. And these are known constants. So they're given constants. So this is a second order homogeneous constant coefficient ordinary differential equation. We're going to solve this the same way that we just talked about. We're going to let y equal e to the mx. We're going to assume that that's a solution. Then we'll compute the first and second derivative. Derivative of e to the mx is the derivative of e to some power is e to that power times the derivative of the inside, which is just m. When you take the second derivative, well, you're just going to multiply by m again, so you get m squared. And then we're assuming that this satisfies the differential equation, so you substitute into the differential equation. The dE was a times y double prime plus b times y prime plus c times y equals 0. And if y is e to the mx, that results in this equation. We've got a times y double prime plus b times y prime plus c times y, which was e to the mx, that was our guess, equals 0. And now, even though it doesn't look like it because we've got these variables a, b, and c, and m there, remember m is just a constant to be determined by us. We're going to find it. A, b, and c will generally be given constants. So this is just a constant times an exponential plus a constant times an exponential plus a constant times the same exponential equals 0. The only way that this will equal 0 is if all those constants add together to give you a 0. Or if you factor out the e to the mx, this is what you get. Am squared, that's the first constant, plus bm, that's the second constant, plus c, that's the last constant, times e to the mx must be 0. Well, e to the mx is never 0, so the only way that happens is if am squared plus bm plus c equals 0. This is called the characteristic equation. Since it was a second order ordinary differential equation, the characteristic equation is a second degree polynomial. Now you just have to find the roots of this polynomial. You just have to find the solutions to this quadratic equation. If you can find the solutions to this quadratic equation, you can find the solutions to that differential equation. Now, when you have a quadratic equation and you're setting it to equal to 0, there are 3 different cases. There are 3 different possibilities for the nature of the roots of that polynomial. So we can think of this not as a quadratic equation, but as an equation defining the roots of some polynomial where y equals am squared plus bm plus c is the polynomial equation that we're talking about, or the polynomial function that we're talking about. It's a quadratic function. So let's talk about the possibilities, the possible solutions to this characteristic equation, and then we'll use that to find the possible or the forms of the general solution to this constant coefficient second order homogeneous linear ordinary differential equation. A lot of adjectives there. Okay, so here's the first case, and we've already seen an example of this. If we're looking at the function y equals am squared plus bm plus c, if I were to graph that in the my plane, it's possible that this quadratic function crosses the m-axis twice. This function crosses the m-axis when y is equal to 0. So maybe that quadratic function, or that parabola if you prefer, the graph of that quadratic function or second degree polynomial, the graph of that polynomial function crosses the m-axis twice. It crosses at m1 and m2. So those are 2 real roots, and they're both distinct. So this function can have 2 real roots. Notation that we use for that is m1 and m2 are in the reals, and they're not equal to each other. Well, in that case, remember you have a second order differential equation, and you want 2 linearly independent solutions. Well, the first solution is e to the m1x. And since you've got 2 real values that are not the same, the second solution is e to the m2x. Since m1 and m2 are distinct from each other, these are 2 linearly independent solutions. So they form the fundamental set of solutions. And since they form the fundamental set of solutions, the general solution is y equals c1y1 plus c2y2. So that's c1 times e to the m1x plus c2 times e to the m2x. And this will work for all real numbers. So that's one possibility. And that's exactly what we saw in that first example. When we solved this quadratic equation, we had 2 values of m that were distinct from each other. M could be 3 or 1. And if m is equal to 3, e to the 3x turns out to solve the differential equation. If m equals 1, e to the x turns out to solve the differential equation. So if you multiply these guys by constants and add them together, you get the general solution. Now, I'm not going to check for you, but if you take this function, actually, let's do e to the x. It's very easy. Second and first derivative of e to the x, or e to the x. If you plug that into this differential equation, you're going to get 0. Second derivative of e to the x is e to the x. So we'll have e to the x minus 4 times e to the x. So that's going to be negative 3 times e to the x plus 3 times e to the x. Negative 3 plus positive 3 is going to be 0, e to the x, so we get 0. So this satisfies the differential equation. Now, if you take the second derivative of this, you're going to get 9 e to the 3x. The first derivative of this is 3 e to the 3x by the chain rule. So second derivative is 9 e to the 3x. Then we're subtracting 4 times 3 e to the 3x. 9 minus 12, that's going to be negative 3 e to the 3x. Plus 3 e to the 3x is 0. So both of these satisfy the differential equation. And then from that superposition principle, if this is a solution of the differential equation, and this is a solution of the differential equation, and we're talking about a linear ordinary differential equation, if you multiply those solutions by constants and add them together, that's still a solution of the differential equation. Okay, so that's what we've got there. And that is a special case of what we have there. So our characteristic equation is defined by the roots, or, well, how do I say it? Our characteristic equation is a quadratic equation. We can think of it in terms of the roots of this quadratic function, the roots of this polynomial. It's a second degree polynomial, so it has two roots. If those roots are real and distinct, they lead to two linearly independent solutions of the differential equation. You multiply them by constants and add them together, and that's the general solution. That's case one. Now let's look at case two. If you've got a quadratic function, it's possible that instead of your quadratic function crossing that m-axis twice, you might be in that special case where your quadratic function, the parabola that is the graph of that quadratic function, just barely touches that m-axis. It touches at one point. So am squared plus bm plus c is equal to 0 at one value of m. We'll call that m1. Now, since this is a second degree polynomial, we're going to think of this not as a single real root, but we're going to think of it as a repeated real root. You'll see how you can tell it's a repeated real root when we look at an example of this case. But this is just the one value of m that satisfies this equation set equal to 0. So m1 and m2 might be real numbers and they might be equal to each other. Then our first solution is y equals e to the m1x. Now our second linearly independent solution can't be y equals e to the m2x, because if y equals e to the m2x, well, then it's the same as y equals e to the m1x, and then we'll have two solutions that are not linearly independent. They'll be linearly dependent. So let's say that m sub 1 and m sub 2 are both 4. Then the first solution would be e to the 4x. I can't say that the second solution is e to the 4x, because e to the 4x and e to the 4x are linearly dependent. They're the same function. E to the 4x doesn't tell me anything that e to the 4x hasn't already told me. So we need a function that is not redundant here. In order to find the second solution, y2, we can say, let's let y2 equal u times y1, where u is some unknown function, and then we can use reduction of order. So I have y2 as u times y1 using, and then we go through the method of reduction of order in order to find the non-zero, excuse me, not non-zero, the non-constant function u that causes u times y1 to be a solution to the differential equation. Now, I'm not going to prove it here. If you want, you can prove it to yourself, and it'll give you an opportunity to practice reduction of order. But it turns out that if you have a repeated real root, m1 and m2, and they're both the same, that u that you would find using reduction of order is just x. So this is x times e to the m1x, and that's our second linearly independent solution. The x comes from reduction of order, which we could prove, but I'm not going to. Okay, so you've got two linearly independent solutions to the differential equation now. In that case, our general solution is y equals c1y1 plus c2y2, because we've got a second order differential equation. So our first solution is e to the m1x, and our second solution is x times e to the m1x. We multiply those by constants and we add them together, and that gives us the general solution. Now the third case might be hard to think of. You say, okay, if I'm setting this quadratic function equal to 0, and I'm trying to figure out, well, what does that represent? Well, what's possible? Well, if I've got this, the graph would be a parabola. The parabola can face up or down. And that parabola, could pass through the m-axis twice like this. So we have two distinct real roots. Or it could pass through that axis just once. It could just barely touch either from above like this, or it could barely touch from below like that. That's another possibility. But you'd have a repeated real root. The third case is that the parabola never crosses that m-axis. So you've got am squared plus bm plus c, and maybe your parabola is up here the whole time. And so am squared plus bm plus c is never equal to 0 in this case. It never crosses the m-axis. But we can still solve the equation am squared plus bm plus c equals 0. What would happen in this case, though, is that discriminant b squared minus 4ac that you have when you look at that quadratic formula, that's going to be a negative number, and you're going to have complex solutions to the equation where this second degree polynomial is set equal to 0. Now, if a, b, and c are all real constants, m1 and m2 are complex conjugate pairs. So we'll have m1 and m2 are alpha plus and minus beta I, where alpha and beta are real numbers. Now, we can immediately write down a solution that looks like this. The problem with that solution, though, is that it will have a complex number in it. So I'm going to put a little star on this. I'm not actually going to use this as my y1 and y2. But if I'm just using the definition, y equals e to the m1x could be my first solution. Let's say m1 is alpha plus beta I. So we would have our first solution as e to the alpha plus beta I times x, and our second solution as e to the alpha minus beta I times x. Now, again, the problem with these solutions is that they have i's in them, and we don't want complex solutions. We want two real solutions to the differential equation. So even though these are solutions to the differential equation, they're not the solutions we're looking for. But it turns out that this solution y1 star is related to the solutions we're looking for using what's called Euler's formula. Now, Euler's formula is something that you will learn more about in complex analysis if you decide to take that class. It says this: e to the I theta is cosine of theta plus I sine of theta. And with that in mind, this y1 star can be rewritten in terms of sine and cosine. In order to do that, let's distribute that x. So I have e to the alpha x plus I times beta x. And notice we have a sum of two terms up here in the exponent. Remember this from algebra class. If you have x to some power times x to a different power, you add the exponents. We can also do that backwards. So if I have a sum of two exponents here, this will be e to the alpha x times e to the I times beta x there. And this part, e to the I times beta x, is the same as what I've got right here. I've got an I, and instead of a theta, I've got a beta x. So e to the I times beta x can be rewritten using Euler's formula. So this piece is cosine of beta x plus I times sine of beta x. And if we distribute that e to the alpha x through, this is what we get: e to the alpha x times cosine of beta x plus I times e to the alpha x sine of beta x. Now, I'm not going to prove it here, but this solution y1 has two parts. It has a real part and it has an imaginary part. It turns out that this real part of y sub 1 star turns out to be a solution to the differential equation. And this imaginary part, which doesn't include the I, it's just this function here, that's also a solution to the differential equation. So we're going to call this our first real solution, and we're going to call this our second real solution. So these two complex conjugate pairs, or this complex conjugate pair, gives us these two complex solutions, but those aren't the solutions we're looking for. These are the solutions we're looking for. So if M1 and M2 are given by alpha plus or minus beta times I, where alpha and beta are real numbers, then the first linearly independent solution is e to the alpha x times cosine of beta x. And the second linearly independent solution is e to the alpha x times sine of beta x. And since we had a second order differential equation, the general solution is y equals c1y1 plus c2y2, which equals c1 times e to the alpha x times cosine of beta x, plus c2 times e to the alpha x times sine of beta x. Okay, I think we've covered all the cases for a second order differential equation. This is because a quadratic function either has two real roots. So these are two real distinct roots. M1 and M2 are both real and they're not equal to each other. Then you get two solutions, e to the M1x and e to the M2x, easy breezy. Or that quadratic function might have one repeated real root. So M1 and M2 might both be the same and real. In that case, the first solution is e to the M1x. The second one can't be e to the M2x because M1 and M2 are the same. So the second one is x times e to the M1x. And then the third solution, or the third possibility, is that instead of having two distinct real roots or one repeated real root, you get complex conjugate roots. M1 and M2 are given by alpha plus or minus beta times I. Because if you set this equal to 0 and you use the quadratic formula, it's possible that you get a complex conjugate pair. Sometimes we get these complex conjugate pairs when we do the algebra that requires completing the square, basically. Okay, so those are the possibilities. Let's look at a couple more examples. Now, these are the possibilities for second order differential equations. Now, remember, with a second order differential equation, you end up with a second degree polynomial equation to solve for M1 and M2. In general, when you have an nth order ordinary differential equation, you're going to have an nth degree polynomial. So instead of solving for M1 and M2, you're going to solve for M1, M2, M3, all the way up to m sub n, because you're going to have n of them, n solutions. If it's a fifth degree polynomial, you'll have 5 solutions. If it's a fifth order differential equation, you'll have a fifth degree polynomial, you'll have 5 solutions. If it was a 10th degree, you'd have a 10th degree, or if it's a 10th order differential equation, then you would have a 10th degree polynomial, and you'd have to solve for m sub 1 through m sub 10. And we'll talk about the form of the general solution later. But now we know how to solve and handle a second order constant coefficient equation using all of these guidelines here. All right, let's do another example. So I've got y double prime minus 10 times y prime plus 25y equals 0. And I want to let y equal e to the mx because it's a homogeneous constant coefficient ordinary differential equation and it's linear. So we will let y equal e to the mx. Then you'll take the first derivative. The derivative of e to some power is e to that power times the derivative of the inside. Then you bring your m down. The derivative of e to some power is e to that power times the derivative of the inside. So we're going to multiply by an extra m. And then we would substitute into the differential equation, which looks like this. Y double prime minus 10 times y prime plus 25y equals 0. And we're assuming that this is the form of the solution. Assuming e to the mx is a solution, y double prime is m squared times e to the mx. Then we'll have minus 10 times y prime, which is m times e to the mx. Then Then we'll add 25 times y, which is e to the mx. You set that equal to 0. Now, if e to the mx is a solution, m has to satisfy this equation. So we'll factor out e to the mx, and we have m squared minus 10m plus 25 equals 0. And exponentials are never 0. So we'll have m squared minus 10m plus 25 is 0, because e to the mx is never going to be 0. So it's for all real numbers x and all values of m. So that's our characteristic equation. Now, before we go further, I think I want to write down the method. We're going to let y equal e to the mx, compute y prime, compute y double prime, substitute into the differential equation and simplify. Then you have a characteristic equation. There's a second degree polynomial. So you've got a second order differential equation, excuse me. So now you've got a second degree polynomial equation, trying to find the roots of that quadratic function. And this one factors pretty easily. Trying to solve for m. So we're looking for two numbers that multiply to give us positive 25 that add to negative 10. Negative 5 times negative 5 is positive 25. Negative 5 plus negative 5 is negative 10. That's the same as m minus 5 squared. That's an indicator, that's squared. That exponent is an indicator that we've got a repeated root. So the solution of this equation is m equals 5, right? The only way that m minus 5 squared equals 0 is if m minus 5 equals 0, and that means that m equals 5. But I'm not going to think of it as m equals 5. I'm going to think of it as m1 and m2 are both equal to 5, because I've got two factors of m minus 5 there. So that's a repeated real root. So you take the characteristic equation and then you solve for m1 and m2, and then you can use any method you want. So worst case scenario, you can always use the quadratic equation. But hopefully, if you see an opportunity to factor, you'll factor. Sometimes it's helpful to complete the square. We'll see that as well. And now we have m1 and m2. And then once you have m1 and m2, you know what y1 and y2 must be. Well, the first solution, if m1 equals 5, satisfies the differential, or satisfies this equation, is y1 equals e to the m1x. So that's y1 equals e to the 5 times x. We take the first and second derivative of this, and we substitute into the equation, we'll get 0. The first derivative of e to the 5x is 5 times e to the 5x. The second derivative of e to the 5x is 5 times e to the 5x times an extra 5, so it'll be 25 e to the 5x. So we'd have 25 e to the 5x minus 10 times 5 e to the 5x. So that's 25 e to the 5x minus 50 e to the 5x. That's going to be negative 25 e to the 5x plus 25 e to the 5x equals 0. So that satisfies the differential equation. But the second solution, y2 equals e to the m2x, doesn't work because m1 and m2 are the same. These have to be linearly independent from each other. So we multiply by an extra x. If I want to know where that x comes from, we can use reduction of order. Reduction of order would tell us that if y sub 2 equals y sub 1 times u turns out to be x every time with this method. So we've got these two linearly independent solutions now because we had that repeated root. You get the e to the m1x, and the x e to the m1x is the second solution. And those are linearly independent from each other because this is not a constant times this. This is x times that, but x is not a constant. So these are linearly independent. So that means the general solution is y equals c1y1 plus c2y2. So that's c1 times e to the 5x plus c2 times x e to the 5x. And that's going to work for all real numbers. So we'll say after you find y1 and y2, general solution is y equals c1 y1 plus c2 y2. And then you're going to state the interval of existence, but with all of these exponentials are well defined all the time. So it will be negative infinity to infinity. All right, so that's what we've got there. Now let's do our last example. And this last example for this video, I want to make it an initial value problem so I can show you how to find the right values of these constants. So we've got y double prime minus 4 times y prime plus 20y equals 0. And we've got y of 0 equals 2/3 and y prime of 0 equals negative 2/3. So that's our differential equation, and those are our initial conditions. Notice this is a second order constant coefficient, homogeneous, linear, ordinary differential equation. So many adjectives. Whenever you see one of those, right-hand side is 0, and these are constant coefficients over here, you're going to let y equal e to the mx. If you don't know what to do, if you do nothing else, write down y equals e to the mx. Then we'll take the first and second derivative. Derivative of e to the mx is e to the mx times derivative of the inside by the chain rule. And then we do it again, bring the constant down. The derivative of e to the mx is e to the mx times the derivative of the inside by the chain rule. Then you substitute into the differential equation. So you had y double prime minus 4 times y prime plus 20y equals 0. And we're assuming that y equals e to the mx is a solution. So if y equals e to the mx is a solution, then this differential equation, or these functions, excuse me, satisfy this differential equation. So we can replace y double prime with m squared e to the mx. Bring the negative 4 down. Y prime is m times e to the mx. And we'll have 20 over here, and y is e to the mx. And we're setting that equal to 0. If we add all these guys together, we get 0 for the right values of m. Now we want to find the values of m that cause this to be 0. So we'll factor out the e to the mx. So we've got m squared minus 4m plus 20 times e to the mx equals 0. And then we're saying the only way that this times this equals 0 is if this equals 0 or if this equals 0. Well, exponentials are never 0. So we have m squared minus 4m plus 20 must equal 0 because the exponential is positive for all real numbers x and all values of m, also real. Yeah, we're assuming that m is real for right now. Ooh. Yes, we're assuming that it's real, and then we're going to let it be complex later. Sorry. Okay, so we've got this equation is satisfied because this exponential is greater than 0 for all the values of m and x that we're interested in. Oh, we're going to let m be a complex number later. Anyway, we'll come back to that, or maybe we won't. Just leave that alone for right now. Let's think about that a little bit. So now I've got m squared minus 4m plus 20 equals 0. You can take this equation and solve for m. So we let y equal e to the mx. We computed y prime and y double prime. Then we substituted y prime, and y double prime into the differential equation. And we simplified. And then after simplification, we had this characteristic equation. Now we're just going to solve this for m. Now you can use the quadratic formula if you want to, but since that number in front of the m is even, and I've got a 1 in front of that m squared, I think completing the square is probably a good bet for this one. So let's complete the square. So I've got m squared minus 4m plus 20 equals 0. I'll subtract 20 from both sides. The number in front of m, we're going to call that b. You want to take half of that and square it. -2 times -2 is +4. You want to add that to both sides. We call this completing the square because adding that to this side makes that a perfect square. So you can do it this way. You can factor traditionally if you want to. Say, what two numbers multiply to give me +4 that add to -4? -2 and -2 will work. And simplify the right-hand side. Or you can say, that was supposed to be a perfect square. What number do I multiply or do I square to get 4? That when I add it to itself, I get -4. It's going to be -2. So you can skip this step if you want to. You can go straight from here to here. That's totally fine. And now we're here. Okay, so we've completed the square. We're trying to get m by itself. So we'll take the square root of both sides. Don't forget the plus or minus on the right-hand side. And over here, you've got m minus 2 equals plus or minus the square root of -16. That's 4i. And then when you add 2 to both sides, you get 2 plus or minus 4i. That's a complex conjugate pair. So we're thinking of this as alpha plus or minus beta I, which means that alpha equals 2 and beta equals 4. Beta is always going to be positive because you're just going to take that number in front of the I, that plus or minus, and absorbs any negative that would be there. Okay, and now since we've got a complex conjugate pair, y1 is e to the alpha x times cosine of beta x, and y2 looks just like it, but instead of a cosine, you're going to have a sine. So we'll have e to the 2x times cosine of 4x, and y sub 2 is e to the 2x times sine of 4x. And then we are one step from the general solution. General solution is, it was a second order differential equation. So you get c1y1 plus c2y2. So that's c1 times e to the 2x cosine of 4x plus c2 e to the 2x times sine of 4x. And this works on -infinity to infinity. Okay, so let's recap. What did we do? We let y equal e to the mx. Take the first and second derivative, substitute into the differential equation. And then you say, okay, let's factor out the e to the mx. That's never 0. We get this characteristic equation. I don't know if you guys can hear my boyfriend's kids like yelling and having fun in the next room. I'm a little bit distracted by them. I'm sorry about that. But you substitute your y double prime, y prime, and y into the differential equation, these choices for y, y prime, and y double prime that we made based on our initial assumption. And you get this, factor out the e to the mx, that's never 0, so you get this. This is the characteristic equation. And then you solve the characteristic equation for m. And you can solve by any method. You could have used the quadratic formula if you wanted to. I chose to complete the square. I like to complete the square. It feels much more intuitive to me than the method of just plugging things into the quadratic formula, even though we know where the quadratic formula comes from. It just comes from completing the square. But yeah, it sort of feels like a plug and chug type thing. So I'm not, well, I think the quadratic formula is pretty cool. It's cool that it exists. I don't like that plug and chug feeling. So we solved this by completing the square, and we got this, and then we're solving for m, so we add the 2 to both sides, and we get the complex conjugate pair because of that square root of a -16 there. So we find out what alpha equals, we find out what beta equals, and then because of our derivation that we talked about earlier, y1 is equal to e to the alpha x times cosine of beta x. So alpha is 2, beta is 4, and y2 looks just like y1, except instead of a cosine, you've got a sine. So that's the general solution. We solved for m1, m1 and m2. Then we have y1 and y2. And then the general solution is y equals c1y1 plus c2y2 on the entire real line. Now, if we did not have an initial value problem, we would be done, but we did have an initial value problem. I wanted to show you how to find the constants in at least one example. So here I'm going to show you how to find the constants. If you don't want to worry about finding the constants, you can skip this and you don't have to watch the rest of the video. that these two initial conditions will allow us to find the right values of C1 and C2. So let's find those. So we're going to use the ICs to find C sub 1 and C sub 2. And the first initial condition was y of 0 equals 2/3. And remember what that means. That says that when x is equal to 0, y is equal to 2/3. So I'm going to replace x with 0 everywhere. And then I'll have an equation that is satisfied by C1 and C2. I'm just leaving spaces for that x equals 0. So I'm replacing x with 0. Sine of 0 is 0. Cosine of 0 is 1. E to the 0 is 1. So this ends up just reducing to C1 times 1 times 1, so that's just C1, plus C2 times 1 times 0, so that's 0. So we just get C1. And we're setting that equal to 2/3. So C1 must be 2/3. You can call it C sub 1 if you want. So we've got C1 there. And then we're going to use the second initial condition, y prime of 0 equals negative 2/3, hopefully to find C2. Now remember what this means. This means that when x equals 0, y prime is equal to negative 2/3. So I need to find y prime first and then replace x with 0 and simplify. Okay, so there's my y. In order to find y prime of x, here I'm going to have to use the product rule. I'll call that my first function and that my second function. Here I will also have to use the product rule. I'll call that my first function and that my second function. So keep this in mind. If they're going to be 4 terms, it's going to be a lot, but it's just a product rule with a little bit of a chain rule. It's no big deal. Calc 1 stuff. Okay, so y prime is the derivative of the first. So we've got a constant times e to the 2x. Derivative of e to some power is e to that power times the derivative of the inside. It's derivative of the first times the second undifferentiated plus the derivative of the second. Derivative of cosine is negative sine of the angle times the derivative of the inside. The derivative of 4x is just a 4. And we're going to multiply that. This is the derivative of the second times the first. Our first was C1 e to the 2x. Okay, so that's this first term in y. And now I want to do the same thing over here. Derivative of the first times the second. Now, notice that when I take the derivative of the first times the second, I'm going to end up with an exponential times a sine function. Since I'm going to end up with an exponential times a sine function, I'm going to add vertically. I'm going to put that exponential times a sine function right below this guy so that I can add vertically. It'll make it a little bit easier to do the algebra at the end. Okay, so I want derivative of the first times the second. The second is sine of 4x. Derivative of the first is that constant C2. Derivative of e to the 2x is e to the 2x times derivative of the inside, which is a 2. So it's derivative of the first times the second, plus derivative of the second times the first. The first is C2 e to the 2x. Derivative of the second is derivative of sine of 4x. That is cosine of 4x times the derivative of the inside by the chain rule. There's an extra 4 out front. So when you add these together, we actually get 2c1 plus 4c2, add those coefficients, times the exponential times cosine of 4x. And then over here we have a negative 4c1 plus 2c2 times the exponential times sine of 4x. That's y prime. But we already know what c sub 1 is. C sub 1 is 2/3. So we can substitute c sub 1 equals 2/3 here. Actually, before we do that, let's evaluate this at 0. Y prime of 0 is this constant times e to the 2 times 0 times cosine of 4 times 0 plus this constant times e to the 2 times 0 times sine of 4 times 0. So you're replacing all of your x's with zeros, and sine of 4 times 0 is 0. So you've got 1 times 0 times something, which is, of course, 0 for everything when you multiply them all together. And e to the 0 is 1, cosine of 0 is 1. And so y prime of 0 simplifies to be 2c1 plus 4c2. That's just in general. And now we're going to set this equal to negative 2/3. And now from here, I think I'm going to substitute my c1 now. From here, I'll substitute c sub 1 as 2/3. So I've got 2/3 times 2, which is 4/3. So 4/3 plus 4 times c sub 2 equals negative 2/3. Then we want to subtract that 4/3 from both sides. So you've got 4c sub 2 equals negative 2/3 minus 4/3 is negative 6/3, which is negative 2. And then you want to divide both sides by 4. So you get negative 1/2. Now you're not done yet, and it's tempting to say that you're done, but you're not done until you write down the particular solution. So this was the general solution of the differential equation. We had to find the values of C1 and C2. We found C1, we found C2, and now we want to write the general solution with the particular solution, the solution that has the C1 and C2 in it. So the particular solution is y equals C1, which we found to be 2/3, times e to the 2x times cosine of 4x, plus C2, which turned out to be negative 1/2, times e to the 2x sine of 4x. And that works on negative infinity to infinity. So remember, this is the function that not only satisfies this differential equation, but it also satisfies these two conditions. When x is 0, y is equal to 2/3, and when x is 0, y is equal to negative 2, or y prime is equal to negative 2/3, or the slope is equal to negative 2/3 at that location. So one more recap. If you have a second order homogeneous constant coefficient differential equation, and it's linear, then you'll let y equal e to the mx, and eventually, after simplification, you're going to end up here at a characteristic equation. Now, a lot of teachers skip all of these steps, and if you're watching videos on YouTube, many people will skip all of these steps and they'll just go from here to here. I choose not to skip all of those steps in my class because I've noticed that when students go from here to here, they don't actually know where this equation came from at all. And for me, that's a bit of a problem. Like, I want you to know why this equation must be true. This equation must be satisfied by m because we're assuming that y equals e to the mx is a solution. So everything stems from that initial assumption about what the form of the solution looks like. So we make that assumption and we don't skip any steps. We're doing everything from first principles, and we end up here. We end up with this characteristic equation for a second order equation. It's a second degree polynomial. And we've got 3 possible cases for the form of those roots of that second degree polynomial. You'd have distinct real roots, which lead immediately to 2 linearly independent solutions, which is great. You've got a repeated real root. Well, then you get one solution. To get the second solution, you have to use reduction of order, but we're going to use a shortcut and say, with reduction of order, guess what? Every time you're going to get x times that exponential. If you don't believe me, you should prove it to yourself. And then the third possibility is that if you try to set this quadratic function equal to 0, it's never equal to 0 in the reals, but it is equal to 0 at some complex conjugate pair, alpha plus or minus beta I. This is where alpha and beta are real, and this is because a, b, and c were real numbers to begin with. Then because of Euler's formula, this complex solution can be written as this part plus I times this part. It's the real part plus I times an imaginary part. And it turns out that the real part of y sub 1 star and the imaginary part of y sub 1 star are two real solutions to the differential equation. We didn't prove that. I just told you that that was true. And I showed you sort of where they came from using Euler's formula, but we didn't go into a lot of detail about what Euler's formula means or where it comes from either. So we found y1 and y2, kind of. I just told you that, hey, these will work. If you don't believe me, you should check it out, substitute them in the differential equation and show that it's true. If m1 and m2 are equal to alpha plus or minus beta I, y1 equals this is a solution and y2 equals that is a solution. It's e to the alpha x, that's e to the real part times x, plus cosine of beta x, and beta is the number in front of the I, just the number, just the real number, not the I. And then y2 looks just like it, but instead of a cosine, you've got a sine. Multiply those by constants and add them together, and you get this. In the next video, rather than talking about second order homogeneous linear ODEs with constant coefficients, we're going to talk about higher order homogeneous linear ODEs with constant coefficients. That's going to require solving polynomial equations of higher degree.